So I did this example on the right in class in relatively detail, but then I told you that we can do the same example by selecting. In this one we selected these loops, okay, but I said you can select different loops as long as they are independent. You can still solve the problem and you will get the same answer. And this example we quickly did it, but I thought that it's good to do it a little bit in detail because some people were asking questions about it. So let's see. I can make this one loop, okay, which is similar to what we did here. It's the same loop. The other loop I can take is this one, okay, because this loop 1 is covering these three elements, okay, but we still have this element and this element, which we can cover by taking another loop, which is, complete loop is like that. So we can do that, right? And they are all the elements are covered, and no loop is redundant, so we are okay with it. They are two independent loops because both are covering at least some elements of the circuit. And let's see we do it with this example and compare our results with the method that we achieved the result that with the method that we did differently here. Okay, so let's see. I take loop 1, I1, which is a fictitious current of this loop, and I start from here, and I know that I'm entering the negative terminal of 12 volts, so I can write negative 12. Okay, then I can take the passive sign convention as well. Then I'm entering this terminal of this resistor, but remember this resistor has two currents going through it, I2 and then I1 both, right? So we have, and both are in the same direction, and the positive direction that we took, which means I have to take the effect of both the currents through this resistor. So I'll write 6 kilo ohm, which is the resistance of this element, and I can write I1 plus I2 in this case, remember, because both the currents are going in the same direction. And then I'll take this element here, okay, remember I'm taking this current, so it will be plus 6k I1, and that should be 0, right? And then I can simplify it, and it will be, when I simplify everything, I bring I1 to the left side and I2 to the right. It will be 12k I1 plus 6k I2, and this is equal to 12. Okay, so this is one of my equation that will help me solve for the unknown. Okay, we have two unknowns, I1 and I2, so we need another equation to have two equations to solve for this. So the other one will come from loop I2 here, okay, and I can start again. I can remember this loop is going, I didn't draw it completely just to make it more clear, but we can start from here, okay, so because this loop is going through this voltage source as well. So yes, we can write minus 12 because we are entering negative terminal. Then I can also put the passive signs on these ones, and then I can say okay, plus, remember this current is going through this resistor, right, as well as the I1, so both of them will have contribution in the developing voltage or dropping voltage across it. So what will happen that I will write it 6k, inside I'll write I1 plus I2, exactly the same way as I did in first equation, because both the currents are in the same direction, so that's okay. So then this current will enter the 3 kilo ohm resistor, and it is entering positive terminal, so I write 3k into I2, and then I'll write it as entering the positive terminal of this voltage source, and write plus 3, which should be equal to 0. Okay, so now I can simplify, and it will be 6k I1 plus 9k I2, which is equal to 9. So remember, this k is equal to 10 raised to power 3. It's called kilo, and we just want to save some space. That's why we wrote it like that. So now we have another equation. Okay, so now we have two equations and we have two unknowns, and we can solve for them. For example, I can multiply this equation by 2, okay, and then I can subtract it from equation A, and doing that will give me minus 12ki2 should be equal to minus 6, okay, and this will give me I2 to be 0.5 milliampere. Okay, so I can just highlight it. So if I have found I2, I can substitute this one in either equation A or equation B, whatever, and I can get the value of I2. Sorry, can get the value of I1, and so what I'll do, I'll put into the one of the equations, and so I'll substitute the I value of I2 into this B equation. Okay, so if I do that, I can do the step a bit quickly. It will be something like 9 minus 9k multiplied 0.5 milli and divided by 6k. Okay, when you do the math, I1 should be equal to 0.75 milliamps. So remember, our job was to find out I0, not I1 and I2. But it turns out that this I0, this time, the way we selected the loops, is equal to I1, because I2 is not going through it. There's only one current that is going through this one, which we found out I1, and I1 is equal to I0, which means our I0 in this case is 0.75 milliampere, which is exactly what we got last time, right? But last time we found I1 and I2 and we subtracted them to get it because our loop choice was this, right? So so this is how we can do same problem through different selection of loop currents, and we still are able to find the same answer as before. So I hope this helped, and if you still have questions, you can ask me whenever I come to the class, before the class or after the class.